All right. Welcome back. So we're going to go into DeepAR. Before we get started, hit the like button, subscribe, and share this with anyone you know taking the Amazon Machine Learning Associate exam. All right. So DeepAR, this is deep learning meets time series forecasting. Right? Time series forecasting represents one of the most ubiquitous challenges across industries. Retailers need to predict product demand across thousands of SKUs. Energy companies must forecast consumption patterns across multiple regions. Financial institutions require accurate predictions of market movements and transaction volumes. Basically, traditional statistical approaches like ARIMA or exponential smoothing have served these needs for decades, but they struggle with the complexity and scale of modern forecasting requirements. DeepAR emerged from Amazon's research into applying deep learning's pattern recognition capabilities to time series problems. Unlike classical methods that treat each time series in isolation, DeepAR leverages recurrent neural networks to learn patterns across multiple related time series simultaneously. So this collective learning approach enables the algorithm to capture complex interdependencies, seasonal patterns, and trend dynamics that escape traditional forecasting techniques. So the architecture, how does this work? All right. So DeepAR builds on long-term, short-term memory, LSTM. These are networks, right? So this is a specialized form of recurrent neural network designed to handle sequentialized data with long-range dependencies. Traditional RNNs struggle with vanishing gradients over extended sequences, but LSTMs incorporate memory cells and gating mechanisms that enable learning from both recent observations and distant historical patterns. The temporal architecture processes time series data through recurrent connections that maintain hidden states between time steps. As the model processes each observation, it updates its interval and internal representation based on both the current value and accumulated historical context. This recursive processing enables DeepAR to capture complex temporal dynamics that static models cannot represent. What distinguishes DeepAR from simple LSTM applications is its probabilistic approach to forecasting. Rather than producing single point predictions, DeepAR generates probability distributions over future values. This provides not just forecasts, but uncertainty quantification. This probabilistic framework enables realistic confidence intervals and risk assessment crucial for business decision making. Okay. So, learning across related time series. So DeepAR's most powerful capability emerges when training on multiple related time series simultaneously. Rather than building separate models for each product, region, or customer segment, DeepAR learns shared patterns across the entire collection while still capturing individual series characteristics. This collective learning provides several advantages. For new products with limited historical data, the model leverages patterns learned from established products, so it enables reasonable forecasts even with sparse observations. For seasonal patterns, DeepAR can learn general seasonality structures that transfer across series while adapting to specific timing variations. For trend detection, the model identifies common growth or decline patterns while respecting individual series trajectories. So the algorithm supports both statistical categorical features that identify series characteristics, like product category or geographic region, and dynamic features that vary over time, like promotional activity, weather conditions, or economic indicators. This rich feature support enables incorporating domain knowledge that traditional statistical methods struggle to accommodate. Okay. Data prep. All right. So this would be something a little more specific. All right. So DeepAR requires careful data preparation in JSON line format. So each line represents a complete time series with its associated metadata. This format choice reflects the algorithm's need for structured temporal data with clear timestamp definitions and optional feature associations. Each time series entry contains several key components. The start field specifies the ISO 8601 timestamp for the first observation, establishing the temporal baseline for the entire series. The target array contains the actual time series values in chronological order, representing the historical observations the model learns from. Optional categorical features captured in the cat array enable the model to learn time series specific patterns. A product ID categorical feature, for instance, can help DeepAR distinguish between different product behaviors while still learning shared seasonal patterns. Dynamic features in the dynamic feat array provide time varying context like promotional indicators or external factors that influence the target variable. So the structure of this tells DeepAR that time series can begin on a certain date. It can contain certain historical observations, It belongs to a certain category, and it shows an experience promotional activity during period 1, 2, 3, 4, etc., which can be indicated by whatever dynamic feature values you have. And the format can also support Parquet for larger data sets, where compression and columnar storage provide performance advantages. Regardless of the format, the key principle remains: provide complete historical series with clear temporal alignment and relevant feature context. All right, so let's do a little bit of hands-on. All right. So let's go to the main. All right. So first, you want to organize your time series data in JSON line format, what we talked about, according to the requirements. Each JSON file it's .json, right? It ends with that. Each file should have multiple lines, each line representing distinct time series, and then have consistent formatting with proper ISO 8601 timestamps. Let's see if we can get a good sample we can show you. Because we're not preparing that, but we're just going to give you a sample. Nope, don't want to go to AI mode. Okay. All right, so data elements, interchange formats. All right, these are the types and forms. Doesn't give you specific date, format, extended format. So it gives you an idea. Let's see. That looks like a decent one. But we'll save that. Yeah, but you can see, all right, it'll have the date, time, like stuff like, identifiers, email addresses, host names, IPs. Yeah, this is not giving me what I'd like. And that's not what I want either. Regardless, you should have a good general idea. All right, but we're in the console. You wanted to upload your prepared data to S3. All right, you can do that there in the console. You can drag and drop, right? The organization should support reproducible workflows. And then for large data sets, you can zip it with gzip and then drop it in your bucket. All right, but we're going to go to SageMaker, scroll down, training jobs, create training job, and then let's name it deep AR test. Remember your IAM role. All right, let's go down. Built-in. Okay, so built-in. So it's DeepAR. Time series forecast. DeepAR. Okay, so we got that one. All right. Yeah, we have our IAM role set up. It has to have the correct configurations for S3, your instance, CloudWatch. Okay, you can see some of the metrics it's going for. Okay, your instance selection. All right, so you want to use the correct instance based on your forecasting scale. You can start with a CPU instance, like the ML M4. It's a good baseline, right? So it'll give you good forecasting workloads and good compute. You can also go up to the, where are they? Did I skip over? Oh no. Let's see. Okay, the P series, right? You could do a P series, which is a GPU instance. All right, so this is valuable for very large models, right? So if you're using something larger than 512, the LSTM architecture in DeepAR will benefit a little bit less from GPU acceleration than other deep learning workloads. So CPU instances are usually going to be your best bet. All right, but I will remind you, DeepAR supports distributed training across multiple instances. So you can have faster training on large data sets, or when you're training many time-related sets and series simultaneously. So you can have this configured to more than one to leverage it, right? And then you can start with a single instances to get a baseline and then, go scale forward. So let's, oops, I'm sorry, not that. It should have been this, 4 instance counts. My apologies. 512. All right. Keep alive period, let's say 24 hours, max runtime, say 6 hours. Max runtime, 24 hours, let's say 12 hours. Custom encryption, we don't want to have a key that we want to apply, but you should consider that. All right. Okay. Network isolation for your own security, VPC, subnets. You basically want to select private subnets, right? And make those available, or you can get your security groups, right? There you go. To make sure this is all working within your system and it doesn't go to any resources that no one has permission to, no one who has, that only people who have permission can use it correctly. Okay, hyperparameters. All right. So the hyperparameters can control the DeepAR's learning behavior, forecasting characteristics, and each one will influence it differently depending on, the accuracy, training efficiency, forecast quality, right? So let's see. Okay, the batch size. So with this one, you're going to balance training stability with memory requirements. So you want to go somewhere between 32 and 256. Well, this will work well, right? Larger batches can provide more stable gradients, but require more memory. Okay, so we don't have anything. So 256 being at the top end, right? So let's stick with that 64 or whatever it was there. Let's see, the learning rate. We talked about this before. So this is how you control the gradient descent step size. So you can start at 0.001 or 1/1000th and monitor training loss curves, right? So if the loss decreases too slowly, increase it slightly. Let's say 0.1, right? And if training becomes unstable, you can decrease it. So 0.05, okay? To basically stabilize the learning dynamics, right? The number cells. So this helps you to define LSTM hidden layer size, right? So values between, I want to say it's like 30 to 100 are typically good. Larger values enable more complex pattern learning, but increase computational requirements and you risk overfitting, okay? You have the context length, all right? So this is how you specify, this is where you specify how much historical data the model considers when making predictions. So this should generally be set to several times your prediction length. So for here, you can provide context. For daily data within weekly seasonality, context lengths of like 50 to 100 days pretty much works well. So let's go for 75 days, right? And then prediction length, right? So this has to match your forecasting horizon requirements. So this defines how many time steps ahead the model will predict. For daily retail forecasting, you want to set this to about 7. For weekly predictions, 30. And then for monthly, no. So for daily, you want to set it around 1. 7 for weekly, 30 for monthly. Yeah. So let's say 30. All right. And then from here, you go down for your input data, where you would store the JSONs. Your train, how did you want to do this? Pipe or file. So on the cloud or with local configuration, right? File is local configuration, content type. JSON, excuse me. Any compression, gzipped or not. Record wrapper or not. Data source, S3. So we'll say file system ID, right? Oh, no, S3. Okay, your S3 bucket, and then your checkpoint configuration if you're running this on spot instances. And then you could also opt for a local path, or you can opt for a local path instead, right? No, you can specify. Yeah, you can do this in addition. Yeah, okay. And then your final output to another S3 or another one with a different folder or subfolder, right? And the spot training, spot instances to save money. Wait time before the job terminates, right? How many minutes? And then you enter your key value pairs for your tags so you know where your spend and your operations are going. And so from there, you want to set up to look in your SageMaker console, your CloudWatch logs, and get the regular updates on training loss, test metrics, and the processing throughput, right? And once successfully completed, you should have a CloudWatch log to give you a notification it's done, right? At that point, you'll get the estimated completion, you'll get done, and you'll be able to use the artifacts and be able to deploy it for production and make your forecasts. We're going to click cancel and close that. Close that. All right. A couple things. All right, cost. So DeepAR's training cost primarily depends on the instance type, the training duration, and data set scale, right? So that's, the instance is going to be the compute, the training duration, that's how the compute workload, and then the data sets, that's S3, right? How much are you importing? How much are you exporting? Ingress, egress, right? So the CPU instances provide cost-effective training for most scenarios. GPU instances are justified only for specific large-scale data configurations with batch sizes exceeding 512, right? So the distributed training can enable faster completion times by spreading computation across multiple instances, but this can increase the hourly costs proportionally. So evaluate whether the reduced training time justifies a higher instance count, and consider both time to deployment urgency and total cost of the ownership of the product in the project, right? And then at a certain point, the four inference costs, right? These are going to scale with query volume and your endpoints. And then you have to right size the instances based on your expected throughput. So you can start with a smaller instance, scale up based on your latency, your throughput, and then consider using auto scaling for endpoints with variable traffic patterns. That'll work with your networking and your instance types. And then for batch forecasting scenarios where real-time predictions aren't required, SageMaker's batch transformation jobs can be used instead of persistent endpoints. And then the batch transformation can process the large data sets efficiently without ongoing hosting costs. So this will be ideal for like a periodic forecast generation, like a weekly demand planning. And okay, so DeepAR deployments require attention to data quality, forecasting, and it has to go beyond just algorithmic configuration. To ensure time series data contains a good data, you have to basically have several complete seasonal cycles to get a robust pattern learning, right? So eventually you'll be able to handle missing values appropriately through either interpolation or explicit marketing. And depending on whether gaps represent true zeros or data collection failures, DeepAR will learn from imperfect data and it can start performing well even with that, right? But it does work best with clean, consistent time series data information, right? So you can regularly retrain models as new data becomes available to maintain forecast accuracy as the patterns evolve, and the frequency will depend really on your domain. So retail might retrain weekly during like a high volatility period, while a slower changing domain might retrain monthly or quarterly. And then you should monitor your forecast accuracy using metrics like absolute percentage errors or mean absolute percentage errors, right? Or weighted quantile loss. And then you can compare DeepAR performance against simpler baselines to ensure the deep learning complexity provides value over traditional methods for your specific forecasting challenges. So DeepAR is basically AWS's smart, fancy approach to scaling time series forecasting through deep learning. So you can use the recurrent architecture, the collective learning, and you can address the forecasting challenges that could typically overwhelm a traditional statistical method. So this requires some careful data prep and computational resources, but DeepAR's probabilistic forecasting and uncertainty quantification can provide a decision support capability that most modern forecasting applications really demand. Okay, that wraps up this one. Next one we'll be going over, well, we'll let that be a surprise. It's blazing text. Anyways, thank you for joining. Remember to hit the like button, subscribe, and share with anyone you know taking the Amazon AWS Machine Learning Associate exam. Thank you. Have a good evening.